Welcome, Monte. Welcome, Nabeel. Dear ladies and gentlemen, welcome to the session 325 in the ZeroBuild forum. This is the last session of the Passive House Day, that's Friday. The theme of the session now is energy efficiency and sustainability in buildings. I am Professor Serdar Ulubeyli. I am a member of the International Board of the Forum. In the session, we have two speakers. The duration is about 6 minutes as planned in total. Each speaker will respectively have 20 minutes for their presentations, and the remaining, the last 20 minutes are for questions and answers. I will introduce our speakers now. However, you can see their LinkedIn profiles by clicking their names in the program page on our website. We are now starting the session by the presentation of Monte Paulsen from Canada. Monte is among Canada's most experienced passive house professionals. He leads a multi-city passive house team that has consulted to or certified more than 70 projects. He has conducted performance testing in more than 600 buildings as well. He is also a passive house trainer who has helped more than 100 professionals earn their certified passive house designer, that's CPHD credential. Monte was a founding member, board member, and trainer at the Passive House Canada. Now, the title of his speech is High-Rise Passive Houses. Passive Houses, yes. Yes, Monte, welcome to our forum and the session. We all are waiting for your address indeed. Good luck.
Thank you very much. Can you hear me all right and see the slides?
Yes, I hear you.
All right. Well, it's a real privilege to be here. Good evening to everyone in Turkey. Good morning from Vancouver, British Columbia. Let's see. All right. So my presentation is very straightforward. I'm going to present on 3 high-rise passive house buildings that are completed, one in Spain, one in the United States, and one in China. And then I'm going to conclude with a few observations about 3 high-rise projects we're doing here in British Columbia that are still in design and will begin construction early next year. I work for RDH Building Science. We have offices in 9 cities in North America. We do building enclosure consulting and facade engineering. We actually have had quite a few people in Turkey at window manufacturing plants, of course, because Turkey is becoming such a leading manufacturer of high performance products. We do energy and sustainability work, including passive house, but we also have done several of the largest net zero projects in Canada. We do research and forensics, and we do repair, rehabilitation, and renewal of existing buildings. We also happen to be the largest passive house team in Canada, working on multiple large projects across the country. We work primarily in the international passive house standard, but we also have people on our team who work in the US passive house standard, who do living buildings, net zeros, and others, and we certify projects around the world. Okay, the first project I want to talk about is Boleta in Spain. Currently the tallest passive house building in the world, and a beautiful example of passive house affordability. This is a very simple masonry building, a construction type I think very familiar to much of the world, and certainly anyone in your part of the world. Masonry, concrete infill. Over the top of what could be a conventional building is rock wool insulation, creating this blanket that basically transforms the building into a passive house, and that's fairly simple to install. It doesn't require tremendous trades training. It needs to be continuous, and the girts holding the cladding need to be thermally broken. Then a very simple cladding mechanism going over the rock wool. The cladding also creates opportunities for the ventilation portals to come through the wall in different places. This is a mock-up of this simple Vinyl windows, again, really common windows. In fact, these type of rehouse frames are made in Turkey and many other places, being one of the most affordable way to do windows in a large project. And ventilation like this. This is not a photo from the project, but a photo of a similar installation of Zender 200 heat recovery units in every unit. I know many of you have been all day learning about Passive House from some of my colleagues at Passive House Institute, and so you've come to understand the importance of triple pane windows and heat recovery ventilation. This was a very affordable project for many of us in Vancouver. The prospect of buying a 2-bedroom or larger unit for only 130,000 euros would be very exciting. And it's the simplicity of the approach that made this an affordable high-rise Passive House project. Really great work by that team. The second building I want to share on is the house at Cornell Tech. This is the tallest Passive House in North America. It's in New York City on Roosevelt Island. And this project, you can see the team that led it there. This is an interesting campus on Roosevelt Island where they have 4 new buildings pursuing different strategies. There's a net zero project, there's a very low embodied carbon project, there's this Passive House project, and Cornell University with this new campus is intentionally exploring different approaches to resilient, low energy, low embodied carbon design. And then we'll monitor them over time and try to learn some lessons between these various approaches. The Passive House building has a fairly straightforward ground floor, sort of a large lobby, bike room, the kind of thing you would expect with a large dormitory. The ground floor also has very large glazed areas. These are thermally broken aluminum windows that allow the view across the river to New York City. As you move upstairs, the student apartments are fairly small, fairly typical student apartments, and this particular university hosts students from all over the world, so they deal with really diverse cultures as people come from many, many, many places to pursue technical education in New York. Here's a picture of a typical student bedroom. You can see the small, we call them mini splits, the air-to-air heat pump system that runs for heating and cooling through the building. Inward opening triple pane windows, fairly simple kitchens in a style that's typical in North America. There's usually an exhaust hood right underneath the microwave there. The Cornell project did a great job of what we sometimes call strategic glazing. They put big windows where they're necessary, but did not overdo the glazing in other places. This is a great example of that. You see the exercise rooms so often have floor-to-ceiling glazing, which is actually embarrassing to some people if they're up on the second floor and someone's looking down rather at an awkward angle up at them while exercising. This project has this really well-placed, simple window that gives a fantastic view back across the river towards the city. And a great approach where we really want to start putting glass where it's needed, where it brings views, where it brings light, where it brings ventilation, but not over-glazing just because we have the technical ability to do so. This is part of what can make larger Passive House projects much more affordable, is this kind of thinking. But again, on the upper floor where there's a fantastic view, go for the big windows. This project used, like most large Passive House, a double wall system with rock wool insulation in both places. It actually had both an interior and exterior air barrier. This entire wall system was prefabricated in an off-site factory. And so these steel-framed panels, you can see one here being lifted, would arrive vertically on a truck off a barge on the site. They'd be craned up into place and attached to the side of the building initially with sort of large hooks. And then workers would go out and bolt them down. If you look at the bottom there, you can see here and here and here, the places where they've been bolted down. And then you see the beginning of the air barrier. They've started to put in the, in this case, Proclima membrane along the inside after all of the insulation has been backfilled in around the attachment points. Note that this is a hanging wall, not a bearing wall. The weight of these units hangs downward. It is essentially the same thing as a unitized curtain wall you might see with a traditional curtain wall building, except with completely opaque panels that are larger. And the risk you face with this sort of thing is that all of the barriers, the air barrier, the wind barrier, the weather barrier, are all in the same location. So it's really important to get the connections right. Mid-construction blower door testing is a bit more complicated on large buildings. You have to seal off elevator shafts and other large areas. But at the end of the day, they ended up with a very elegant, simple enclosure on this project. Window to wall ratio of about 25%, give or take. So the glazing area is about 25% of the total. And of course, the lower glazing areas, while still providing great views, is one of the keys to making large Passivhaus projects affordable. Lots of thermal break products. So you see here and here these thermal breaks so that the overhangs don't create a thermal bridge back to the building. Here's another space where you see these thermal bridges on the roof for the equipment and other pieces happening up there again, and then there'll be insulation placed around that. Most large buildings use large ventilation systems. This used a single heat recovery ventilator on the roof, so different from the Spanish project we saw earlier, which had a small one in every single unit. This had one very large HRV outside. It creates some challenges to performance assessment for certification, but these are certainly surmountable in a large-scale project. In most cases, we're seeing large buildings use large units like this, but not universally. And then a regional heat pump system for cooling and heating with an outdoor condenser placed on a little balcony here, and then a local unit in each apartment. It was important, again, because this building was hosting students from all over the world. People have very different expectations. Some people consider 35 the normal temperature. Some people consider 30 a normal temperature. Some people from Canada consider 16 or 17 a normal temperature per unit. And so it had to be able to produce these different results. This is a look at the balcony where the outside units for the heat pumps were placed. You can kind of see from the outside, it's this strip, and from the inside, it's this series of small ventilated rooms. So all in, it's becoming a really interesting campus, a really interesting focus of sustainability, and frankly, a really beautiful site on Roosevelt Island, right off the river from Manhattan in New York. The third existing project I want to talk with it is while not the highest, certainly the largest Passivhaus project in the world in Gaobeidian Railway City in Hebei State, China. This is 16 high-rise towers plus 14 mid-rise buildings and a variety of low-rise amenity buildings, more than 1.2 million square meters of certified Passivhaus by the developer Long4, who is looking to repeat this project elsewhere in the world. The Chinese, as they often do, have basically a large park with some repetition between the buildings, creating great affordability. These are upper-end owned apartments. This entire complex is very short walking distance to a high-speed rail station. From the high-speed rail, one can be in downtown Beijing in the range of 20 minutes. So for families with resources, it's an affordable housing option just outside Beijing. This looks at sort of the central plaza. You can see the buildings step down as they work towards the private park space and play spaces open. The entire project attempt to use more permeable soils so that it is not as hardscaped with as much concrete as you would see in many others. And we're seeing many Passivhaus projects also pursue these other sorts of sustainability goals at the same time. Each entrance is a little different. To keep some variation, even all the overall buildings are the same. The entrances are a mix of some actual stone and some sort of fake or purpose stone where you basically have plaster over foam insulation. On the upper levels like this, you can actually see the plaster over foam fairly clearly. Let's see if this will play. And you can actually hear when you knock on it at times that there's a bit of a hollow sound where there's. So it's at the upper levels, it's clearly meant to be a more affordable approach to actual stone. But a huge project with great affordability points, great exterior shading to keep the projects cool and help lower the cooling load on all the units. Each unit has a local heat pump or air-to-air source heating and cooling device. In China, it's strongly preferred to have local units rather than centralized units. So if there's any problems, the owner of the unit can find a supplier and have it fixed themselves. And so increasingly, you see these little tiny balconies for individual heat pumps rather than having them just bolted on the outside of the building, as happens so commonly in retrofits. Every unit has its own small heat recovery ventilator. So again, not the centralized system like we saw in New York, but something more like the Spanish system. The photo on the left is the ceiling access panel in the kitchen where it sits. The photo on the right is of the unit, but a demonstration unit, not the one actually in the building. We find residents in China, especially in the area around Beijing, are highly aware of air pollution. They're dealing with air pollution on a daily basis. The numbers change. And so if you look at the thermostats or the control units in their apartments, they're actually displaying real-time readings of small particulate matter called PM 2.5 or CO2 in the unit, as well as temperature and humidity all the time. This awareness of the importance of ventilation in some ways makes many Chinese apartment buyers a little more sophisticated as purchasers than at least we see in Canada and the United States. And Chinese love to cook food that's fairly aggressive in terms of its spices and grease. So they tend to have flow-through ventilation in the kitchen and extract ventilation in the kitchen. In North America, we often cook a little more lightly and we do recirculating kitchen vents. What you're seeing here is a vent here that exhausts to the outdoors of the building and then actual gas cooking units. The kitchen is on a door from the rest of the unit, so you don't have exchange with the rest of the apartment from the cooking noises. And again, given their preference for local systems, they actually have very local solar hot water heating systems. Each unit has its own tank. Here's one in the closet. Most of the units have their own solar panel, solar, not photovoltaic, but solar thermal for the hot water, with then some electric resistance backup in case the solar thermal doesn't provide enough heat for the amount of hot water that's used. The electricity can kick in and pick up the rest. So again, a real strong approach to affordable, repeatable units. And the side benefit China has is that because it's making these components at the apartment scale rather than the whole building scale, the component market has become competitive. There are multiple providers of great windows, great small energy recovery ventilators, great small hot water systems. This gives them the component supply they will need in the coming decade as they undertake a sea of retrofits, retrofitting many of their older buildings to more energy efficient standards. And again, already the largest passive house project in the world, but it has plans at that project to nearly double in size, and the developer Long4 looks to do this elsewhere. And I'd like to wrap up just briefly with a look at 3 buildings not yet constructed that our team is working on here in Vancouver, Canada. Mention really briefly, Alberni Towers is a more traditional project, not unlike those you just saw. It will be concrete frame, heavily clad on the outside. It's built by Asia Standard Americas. It's actually a partly Chinese-backed project. But by Robert A.M. Stern Architects, a very traditional New York architect who's done many of the signature apartment buildings in New York. A2M as the passive house consultant in Belgium, so it's a truly international team. And we at RDH Building Science are the building certifier in this project. This is due to go into construction next year. And while it will be the largest passive house project in North America by far when it's made, it's 48 stories, the high tower on the right. Its construction methodologies are fairly known. Another tower I want to show you briefly, we call the Earth Tower, is very different, a bit shorter. This is passive house and mass timber. So there would be some concrete at the foundation and the frame, but most of this tower is actually to be made of wood. This is an example of the wood framing on another project. I just want to show you how it works, though, that we'll have wooden cross-laminated timber panels and frames. And because the wood construction has the risk of being exposed to water or fire or other damages, it's essential to enclose the outside very quickly, keeping up with the wood construction. so that it doesn't get damaged during construction. And that drives us to a panelized approach, similar to the one we saw in New York, where we have large panels that come in and connect on buildings of this type. We're doing several large timber high-rises. This gives a sense of the time frame, whereas you can watch sort of another story of wooden deck planking. This is the cross-laminated timber every day or two, and then the enclosure keeps up just a few days behind to keep the materials safe and dry. It certainly takes more time to prepare this type of construction, but the framing and the completion of the enclosure happens very quickly in this particular building in a period of approximately 2 months. This could typically take 6 months construction under other circumstances. And in some ways, we see this as the future of this integrated curtain wall systems, that we might see a wood platform, as you see there, then wood-backed panels, much like the ones we saw in New York, except different, heavy exterior rock wool with pieces mounted in, and they still have that expansion joint. We sometimes call it a chicken head here, just as unitized curtain wall has, so the building can move in wind with earthquakes and other conditions. This just gives a sense of kind of what that might look like. When we build these, it's often necessary to change them at the corners because the different shifting loads prevent you from creating two large panels meeting in the corner. And so the designs of the corners and the connections becomes really important so buildings can continue to move. And of course, while the inside is made of wood and the panel itself is made of wood, the outside could be clad in any way you choose. We do have one project that is also hoping to clad the outside with cedar in this somewhat basket-like format. This is a building for First Nations, or what we call our Canadian Aboriginal groups housing here in BC. I would note at RDH Building Science, we have several specific guidelines about tall wood. So if it's something you're interested in, feel free to get in touch with me or someone else at our firm, and we can help you with that. And finally, got a few minutes left. 1075 Nelson, when finished, would be the tallest passive house project in the world at this time. It'll be 60 stories in height. Hanson Development is the developer. WKK Architects, Tom Wright is the architect. This is the same guy that did the Burj El Arab in the Middle East. And we are the passive house consultant, facade designers, and other pieces. This building, while it's vertical, will be a mix of community. There will be social housing on the bottom 15 floors, market rental housing in the lower area, and then luxury-owned apartments in the upper regions. The facade will be quite challenging. It looks like a lot of glass when you first look at it, but if you look closely, you'll notice that there are sort of glazed sections surrounded by opaque sections in between, giving the sense of a lot of glazing area, but the actual total glazing area is slightly less than 45% on this project. Working it out through the curves has been a real challenge to figure out how to fabricate that. And the approach we're pursuing at this time looks something like this. We will build a steel frame structure that will niche and nest, and so they would either go over each other or under each other as they work their way up and down the curves. Over that would be installed window bucks to hold the window into the frame in a thermally isolated way. The windows would then install into those bucks. There would then be insulation, exterior rock wool insulation in thermally broken attachments outside of those. And then outside of the insulation is cladding that is also made of glass. So it gives the impression that there's a solid line of glass across the building, though in fact it's not all opaque. Much of it's, it's not all transparent, much of it's opaque. Then additional insulation at the top and bottom, that metal band that goes over that, and that allows us to have the step either coming out or coming in, depending on where you're at on the building for the curve. And it all comes together to look similar to what you saw on the rendering before. It's definitely a signature building in Vancouver. It's one of the tallest sites in Vancouver. In addition to being one of the tallest passive house buildings in the world, it would be the tallest building in Vancouver just by a few meters. The building next to it here, called the Butterfly, is another project working on, although not passive house. it's been a real pleasure to present to you. I hope there are some great questions. I look forward to hearing the next presentation. If you have additional questions or things you want to follow up on, my email's there. And really, I just want to end with congratulations to this great forum for doing a Passivhaus Day and for beginning so many of these conversations. While I've presented here on high-rise technical Passivhaus buildings, I hope what you've heard all day is that Passivhaus can be very affordable and very practical on many different building types. Thank you.
Thank you, Monte. Actually, we are strong with you, our speakers. Thanks really very much, Monte, for giving a precious viewpoint for high-rise passive houses. In fact, many people imagine a small, a single-story, cute, lovely house when one uses the phrase passive house because of the word house instead of building. However, you now reset and then subsequently format the minds. Thank you very much.
Thank you for having me.
Now we will listen a speech from Nabeel Sıddıqi from Pakistan. Nabeel is a social innovator and a CEO. He has a background in civil engineering and project management. His startup in Pakistan works in making sustainable off-grid housing facilities. Yes, Nabeel, welcome. Our participants are eagerly waiting for your speech. It's your turn.
Thank you, Professor Serdar. And it was amazing to see what Mr. Monty presented. What was really interesting that he's been able to do with high-rise what we're doing with low-rise structures. So it might be a different kind of presentation, but I feel we're targeting different areas and might be interesting. Can you see my screen? You can see my screen now?
Yes, I can see.
All right, so I'll give a bit more background about myself. I started this company right after graduating, and we were inspired by, in fact, a refugee crisis around the world. Back in 2016, we saw the Syrian refugee crisis, and as an engineer, what I witnessed was that one of the biggest problems they were facing was, in fact, housing. Because these people, they could not go back to their, they could not be rehabilitated. And what we noticed was that whatever construction technology that existed, it either cost too much or took too much time, or did not provide proper living conditions. So that's how we started with this idea of providing sustainable living while being dignified and cost-effective. So my journey once I started this journey, it wasn't just limited to the Syrian refugee crisis. We saw that all over the world, there was a huge crisis in terms of affordable housing. It wasn't limited to Syria. All around the world, there were over 1.6 billion people that lack adequate housing. And even though that housing is such a basic need, there was not much that current technology can do. There's a McKinsey study that says in order to address this issue, we invest $11 trillion in construction costs alone. And that's what I found really troublesome. But let's say we do manage to get those resources, those capital resources. The biggest issue that we see is that looking at the scale of the issue is that if we continue to build the way we do today, it's going to push climate change beyond the tipping point. So whatever we have to do, it has to be extremely sustainable and cost-effective. So this is how we set vision for our company, and I'm going to run you through a product development cycle that we went through. And this is how, based on these few metrics, we decided that whatever we have to do, it has to provide dignified living, provide at least basic living standards to the occupants, And we want to create houses that can reach the most amount of people. So these are people in high population countries and people that currently lack housing, even basic housing. So we want to reach the most amount of people. Thirdly, the solution must be cost effective. And fourthly, it must be sustainable. So we push climate change beyond the tipping point. So these are the four primary objectives we started with. And what we really struggled with initially was that what is stopping the world? Like, there is ample technology available out there, but why do we not see zero energy buildings being more widespread? So this is how we went through that investigation where we saw, okay, what are the barriers around zero energy buildings? Why we can't make them more widespread? So first thing we did was we started identifying specific pain points. We started talking to a lot of organizations working in affordable housing. Also, we started talking to a lot of end users and contractors as well, because let's say we do get a really good solution, but there's a lack of skilled labor, for example. So I'm quickly going to run you through the most common pain points that we identified. Number one for most people is affordability. Similarly, the quality and the comfort of the house, how safe you can make that house, how the environment of that house can provide you with better living conditions and result in better mental health, and as well as development of children. And a lot of these countries that we work with are developing countries with limited resources and limited water and energy. So how do we provide water and energy sustainably to such a large population? So these are some of the pain points we start with. So we identified the most common pain points and we started prioritizing them. And then we started giving them a score in terms of their reach and their impact. By reach, we mean how many people this particular feature can affect. And by impact, we mean so how much difference it can make in one person's life if we really solve this problem. So this is just an example of how we set out to do. And we started giving a score for every pain point. Next thing we did was that we started looking at current technologies available, and we came up with this moonshot idea that should meet all these conditions. And it's confusing because if you look at the vision, if you want to provide really good standards of living, you have to compromise on cost. And if you want to provide something that's very sustainable, again, you have to compromise on cost. So that's the kind of problems we were looking at. So the next step was that we started identifying different solutions available on the market. And this is specific to markets. There can't be one such metric globally. It depends on which markets you're looking at. We initially were looking at developing countries and places where there's abundant land and inexpensive land. So to give you an idea how we started calculating this, we took a metric such as, let's take the cost metric, for example, which has a score of 25. And we took a relative score of an existing construction method or technology. So let's say there's a housing technology that costs half the most expensive yet viable construction technology. So that gets a score of around 50%. And then you multiply the metric score by that relative score and you come up with a technology score for that specific metric. Similarly, you sum up all these metrics, and this is what we came up with. So we looked at the most commonly used construction methodologies, as well as our own that we were developing. And we saw that prefabricated buildings were actually quite far ahead compared to other kinds of construction available. We looked at 3D printing, and we got a lot of data and we worked around with that. So in the second part of the presentation, I will share what we did that got us a higher score than other technologies. So this is us, and our score is around 84. And again, there is no limit to the score, but we got a higher score than the other technologies available. So the solution was simple. We designed a house that's net zero energy. is cost effective, meets all the metrics that we have. And then we couple it with solar based mineral water purification systems, as well as solar energy systems to provide clean electricity for these houses. So the first prototype we came up with was a 1-bedroom studio costing as low as $3,000 and could be assembled in a day. So imagine a house that you can unbox and set up yourself within a day and could last more than 30 years. Some more features of the house were that they followed, all our designs follow international building codes in terms of their architecture and structural strength, so they're resilient to earthquakes and strong winds as well. We utilized a very resource-efficient design and something that was very fast to build, because labor cost in a lot of countries is really high, and we decided in order to minimize the cost as much as we can, we have to reduce construction time as well. Similarly, we kept to design something that's very DIY, do it yourself, and modular, so people could build these houses themselves and they wouldn't require any heavy machinery or cranes, for example, because that also comes with a large cost. And then we kept the buildings energy efficient, and again, we're designing them for moderate to hot climates, so our values are moderate, not extremely high, but something that's a balance between the cost and the resistance insulation. We also decided to keep the design flat packed, and the reason for that is we saw us working not just in one country or one region, but being widespread, and the solution we came up with so industrialized that if it was flat pack, it would be easier to transport and more economical to transport the houses around. So all these features, they somehow add up to be a house that looks something like this. It's a flat pack structure. You can ship it anywhere around the world, and you unpack it and it's assembled very quickly, and then it's connected with electricity and water. So it becomes a completely off-grid structure, autonomous, with its own electricity and water. And this process takes around 2 days. First day you assemble the house, and the second day you're done finishing the add-ons and the finishes. So we can pack 11 such houses in a single 40-foot container. Again, that adds to the economics and ease of transport of the houses. We've done bigger units as well, 2-bedroom, 3-bedroom houses. For that, we can pack a few less houses per container. But again, the per square footage transportation per container is around the same. We've initially calculated the embodied carbon, and we compared it to some of the most commonly used construction methods, and we found that we were 90% lower than what was being used most commonly in the market. And then the add-ons is where these houses become net zero energy over their life cycle, because they're contributing more than the kind of carbon they're using. So we added this. This is actually a machine that we're using from a Turkish partner, so it's manufactured in Turkey. What this machine does is it purifies any kind of water into mineral drinking water, and it runs completely on thermal solar panels. So it can take something like industrial waste and convert it into drinking water. And again, it's very cost effective, and I'd be happy to share the details of this company as well. Then we have some more partners that have these AI-enabled smart microgrids. What they're doing basically is sharing solar energy between the houses. So each house has a shared system of solar energy, but then they're also linked with satellites, and that's how these units, they can calculate how much energy to save and how much energy to give back to the grid. So that adds to the cost effectiveness of the solution. And again, each house comes with IoT devices, so they can calculate the kind of thermal comforts that are required. So this is where we stand today. We've come up with a house, we've coupled it with water purification systems, we've coupled it with energy, and now we're one step away to creating autonomous living communities. And we'll be building the first one very soon in Pakistan, and we're looking at the African market as well. So this is what keeps us going, is that something such as social green housing, it has so many impacts. It can help with economic development. It indirectly helps over 10 UN SDGs. And this is why we feel that zero energy buildings should be the future as well. Thank you very much. It's been an absolute pleasure. And I look forward to any questions, and you can always reach me out on my email or visit our website as well. Thank you.
For your nice presentation. I think especially the adaptation of the latest technologies such as artificial intelligence and the Internet of Things to zero energy buildings in practice is very valuable. Now we can take some questions from our listeners. As I see, there's a question to Monte. Monte, the question is that we are not used to constructing with wood. We would be very interested in learning more about the wood exterior cladding systems. How could we get hold of the book?
Two ways. There are groups such as Woodworks in the US and Canada that have libraries online with quite a bit of material about wood construction. By the way, great presentation, Nabeel. I really enjoyed it. Our mass timber buildings use roughly 25% less embodied carbon than our concrete buildings. And so that desire to lower the embodied carbon is a big drive of learning to do high-rise timber. The RDH books, you can also send me an email, mpaulsen@rdh.com. I'll try to find a link I can put. I'm not sure I'll find it in time to get it in the chat, but if you send me an email, I'll be happy to share a link.
Okay, thank you. And the question, there's a question for Nabeel. Nabeel, the question is that, what do you think about the future of prefabrication in the construction of buildings instead of houses? Since I think, as we see and understand, your company is putting the prefabrication to the first order in your supply chain and marketing works. And the question is continuing, will there be 100% prefabricated green buildings in the future? What is your expectation in the following 10 years, 20 years, 50 years, or maybe never?
It's a great question. I feel that with the current technology today, a solution that is industrialized and can be mass manufactured, such as prefabricated buildings. And again, we're discounting the fact that these prefabricated building factories can run on solar energy as well, so you can further optimize the emissions. So I see that as the leading way we can build housing at large, especially for affordable housing, as well as some buildings. In the future, we're yet to see 3D printing catch on and become more economical and easier to use as well. So let's see how it goes.
Actually, Monte, as a passive house specialist, we can direct the same question to you to have your viewpoint. What is the future of totally prefabricated passive buildings? What is your forecast in this respect from the passive house side? Yeah,
I think we have to get over some market and supply challenges, but it's a big future. We see it's where it's going. We have worked on 6 or 7 completely prefabricated passive house buildings, ranging from small, affordable townhomes, like 6 identical units, to we're working on a project now that's 6 stories and about 50 units. These are mostly volumetric modular, meaning there's an entire wooden box that's shipped and stacked on site. The volumetric modular approach is less expensive in remote sites, Northern Canada, First Nations communities, poor communities where you don't have trades. It's closer to the cost in a city where you have competition for labor and competition for supplies. However, that point is moving forward. We also see a future where the prefabrication will be a little bit more sophisticated. So instead of being, say, all volumetric, you might have some mass timber planks and panels. You might have prefabricated wall panels, but you also might have prefabricated like kitchens and bathrooms and hallway and mechanical chunks. And so rather than being all boxes from one manufacturer or all panels from another manufacturer, it's a more artistic blend. Right now, a lot of architects and developers are still excited by one or the other technology. And they're like, oh, let's do mass timber, or oh, let's do prefabrication. And we think the mature approach is going to be an affordable blend of the best technologies as needed by the specific building.
Maybe the 3D printing technology is becoming very popular now, but it is somewhere not a major position, but maybe in the future it may be our future.
Absolutely.
Yes. One more question. Yes.
I think the 3D printing is very climate specific. So in hotter climates where insulation is less of an issue, I think it's a fantastic solution. It can be really affordable. We would have difficulty overcoming the thermal bridging and seismic issues with 3D in Northern Canada, whereas we have a lot of wood, these giant forests. So I think it's okay. And to get back to that sort of ancient idea that we build out of our local materials for our local climates wherever we are.
Yeah. Of course.
I also agree with what Monty said.
Okay. Nabeel, you will say something about this issue?
Yeah, I absolutely agree with Monty. So having a product approach to housing with, again, MEP systems being inbuilt as well is, I feel, the future of where we're headed or should be heading.
Thank you. One more question to you, Nabeel. You said that we can move the modular houses you build to anywhere. How can you balance and uniformize your energy calculation when the north facade and the south facade are different?
Yes, so this is a problem you face with a product approach. Generally, buildings are designed for one location, and when you're designing for different locations, it becomes a bit of an issue to optimize that design. So what we've been able to do is we've been able to come with two variants, one for colder climates and one for hotter climates, and based on the latitude, we determine what kind of solar geometry we can incorporate in the design in terms of the passive design of the houses and how we place the windows on sites where there's less sun and less glare coming inside the houses. So that's how we design each product. That's one of the passive strategies that we use. Again, there are a lot of other things you can do as well.
Nabeel, is there a question? I think no. Another question. I'm looking at the private chat. Okay. No questions. Okay. We especially thank our two speakers of the session. Thank you very much, Monte and Nabeel. You have made an important contribution to the forum through sharing your views and presenting your practical applications in the industry. They are really very precious for us. We can end the session now. Dear our listeners, see you on Sunday in the last session of the forum. Bye.
Thank you.
Thanks so much. Thank you.
Bye.
Bye.